Today, the workshop is all about NCS, nerve conduction studies. So, what is a nerve conduction study? A test of the peripheral nerve to record non-invasively the functionality of the lower motor neuron, which means after it has left the spinal cord. This is your spinal cord, right? You have your dorsal column, you have your ventral column, then forming the nerve root. That's your sensory, and this is your motor in your spinal cord, the cross section, right? And there are synapses here. So this again can be replicated bilaterally, left and right. Right? So the ability of this test is to detect any functional issues relating to demyelination, secondary degeneration caused by trauma, or toxic neuropathies, metabolic neuropathies, which could affect motor or sensory pathways, is what we're going to do today in the workshop. So I will start today with motor nerve conduction study, and we will do one upper limb and one lower limb nerve. The same we'll do with one sensory nerve in the upper limb and one in the lower limb. There are many subtypes of nerve conductions which we can do also. Some of them, they are called as late responses. Late response, which is, anyone? What is the late response? FA. Anything else? H. Anything else? Blink. Very good. So these are myelinated fibers, all of these. We have the ability with this particular systems to record even from the unmyelinated C fibers. These are afferent fibers. So afferent and efferent, let's clarify the definition, what it means is. Afferent fibers are sensory fibers, all right? A, F, F, E, R, E, N, T, afferent. And these motor fibers are referred to as efferent. What it basically describes is the physiological conduction path in which they send the information up to the brain through the spinal cord or descend down, right? A motor response, for example. Motor is an efferent fiber because the action potential is initiated through the motor cortex, through your voluntary control. You basically act on the particular muscle, that is, your body acts on the particular muscle, doing it by extension, flexion, adduction, or abduction. These are all mediated through efferent function of that peripheral nerve. The afferent fibers are just the opposite physiologically. And that is important because that is why we change the polarity of the stimulator from anode to cathode, or cathode to anode, because of the sensory function we are trying to test. That is again in H reflex and F waves that we see this happening most often. All right. So the afferent fibers are sensory, meaning the sensation is initiated from the peripheral nerve. It travels up to the sensory cortex to the brain through the brainstem. Let's talk about the characteristics of a motor response. Motor response is usually about 10 times larger than a sensory response in amplitude. They are usually in the order of a few millivolts. Sensory responses are in the order of a few microvolts. Hence, the parameters for recording these are very different from these. Okay? Things to consider, not only our amplitude, but also the time it takes for each of these nerves to conduct. And that's important. Why? Because, like say you have a patient with demyelinating disease, acute Guillain-Barré syndrome, right? You do your setup, you do your recording setups just like how we normally do a nerve conduction study, or say on a peripheral nerve such as APB. You're recording off the APD, which is abductor pollicis brevis, supplied by the median nerve. You do not see a response on the screen, but you know the clinical condition affects myelinated fibers. Then the first thing that it should click in your head is it possible that the demyelinating condition is so bad that is beyond the normal timeline of the normal window that we set it up at? Typically, we have a nerve conduction study settings in the sweep speed, if I was to talk about, around 2 to 10 milliseconds per division. And the sensitivity would be anywhere from 500 microvolts to 1 millivolt per division. That will be the vertical sensitivity. To change the sweep speed so as to accommodate if this is further down, to see if you can compress and bring those late signals caused by the demyelinating condition. So that has to be in the back of your mind. And same with the sensitivity. Because the signal is so low, the demyelinating process has caused so much damage to the nerve, you will not visualize it right away until you jack up the sensitivity. Confounding factors, which can change a normal study to an abnormal study. Temperature, very good. Temperature. Ideally, we should keep the temperature at around 31 degrees centigrade, skin temperature. Hence, we have this thermometer here. You attach this to the skin before we start the study, and that gets recorded onto the software, and that would not only indicate to the person interpreting the data, but also if the temperature was very low and it was a setting such as in a condition where you cannot heat the limbs, what do? You can convert with a calculation of 1.5 meters per second per degree centigrade. So with that, if it was 29 degrees centigrade and you want to convert it to what it would be at 31, the discrepancy is 2, so 3 meters per second. So today we're going to do a motor and sensory in the hand. We'll choose the median nerve, right? It's easy to do. We can choose ulnar as well, but we'll start with median. We'll go about testing the median nerve. I will try to introduce some artifacts later on to show you how things change. We will do a median sensory from all the digits that are innervated by the median nerve. Okay? I think we'll do an ulnar as well. For the legs, we'll choose a posterior tibial nerve. That's again easy to do. And we'll also do a common peroneal nerve. We'll do a sural nerve and a superficial peroneal nerve. Okay? That's a tall order, but we should be able to accomplish that. So volunteers, please.
Christine. Oh, yeah, she's already there.